All right, so today we have Anirudh Deb, who will tell us about the nilpotency index for 4D n equals to 2 SCFTs. Take it away.
So, hi everyone, and I thank you all for inviting me to your Quiver meetings. And indeed, I'll talk about the nilpotency index for 4D n equal to 2 SCFTs. This is based on a paper which we put a few months ago with Carlo Meneghelli and Leonardo Rastelli. So, is it not working? Okay. So this is roughly the outline of the talk. I will give an introduction, which will be pretty long, and then I will basically give you a few quick glimpse at our results. And finally, if there is some time, I can discuss the classification of theories with this nilpotency index equal to 1 or 2. Okay, so first, I don't know how much of VOAs people over here know, so I'll also go over it briefly, and you can stop and ask me something if there is any confusion. Okay, so I guess in this meeting I don't have to say that 4D n equal to 2 SCFTs display rich mathematical structure, and there are these long-standing research programs which aim to leverage the rigidity of these structures to classify these SCFTs. So one of them being done by Philip for rank 1 and rank 2 theories. So the main topic, there are two main branches for these theories. These are these Coulomb branch and the Higgs branch. The Coulomb branch is where you have U and R symmetry broken. So for example, if you give a wave to a scalar of n equal to 2 vector, you are moving on the Coulomb branch. Similarly, for the Higgs branch, you break this SU to R symmetry. In this case, you give wave to scalars of the hypermultiplet. And in many cases, like these branches are more accessible in certain cases where other aspects of these theories are not. So for example, this Coulomb branch business has been a very old one and has been the subject of study of Seiberg-Witten theory since Seiberg-Witten introduced it in their paper in '94. And then recently, there has been a conjectural correspondence between the Higgs and the Higgs branch and the vertex operator algebras corresponding to 4D SCFTs, for which we had like a meeting in which some of you guys were here at Stony Brook. So in general, these two branches are sort of unrelated, and there is like no clear conjecture as to how these two branches are related to each other. Also, like we don't know so far of like two SCFTs which have the same VOA data and the Coulomb branch geometry data. So as I said, like there is this well-developed classification program which leverages this Seiberg-Witten geometry. And in this case, the theories are arranged by increasing rank, where rank is the complex dimension of the Coulomb branch. And in Lagrangian theories, this basically is the rank of the gauge group. So for the rank 1, this classification is complete. It was done in a series of papers by Philip, Lotito, Lu, and Mario during I think 15-16. And a comprehensive analysis of rank 2 has also been is also like, I don't think it's like complete, but it's very close to complete, I believe, by Philip and Mario in 22. So a different approach which
maybe I can interject.
Yeah.
It's not really close to complete.
Oh, it's not close to complete. Okay, thanks.
I mean, from a mathematical point of view, there are many open questions.
Okay, okay. Thanks for that. I didn't know that. So one can take like a different route to try to classify these things, and that would be using the Higgs branch or the VOA point of view for these theories. But from the point of VOA, it's rather less obvious as to how to do this thing. So before moving on, I'll do a brief recap for viewers, so hopefully everybody's on the same page. So yes, so there was a map conjectured in by Beam, Lemos, Lendo, Pilas, Rastelli, and Rees, which associates a VOA to a 4D SCFT. This is obtained by passing to the cohomology of some nilpotent supercharge. So the details are not important, but there is a nilpotent supercharge whose cohomology gives you this VOA. And as a vector space, this VOA consists of what are called Schur operators, which satisfy this, whose quantum numbers satisfy these shortening conditions. So where E is the conformal dimension, J1 and J2 are the Cartan eigenvalues of this SU2 times SU2 rotations, and capital R and small r are the for the SU2R and U1R symmetries. And this VOA is graded using these quantum numbers. So there's this H, which is basically the two-dimensional like conformal weight of the operators in the VOA. And it's like a function of this four-dimensional quantum numbers. And then you have the SU2R and the U1R Cartan eigenvalues, using which you can grade this VOA. So there's a small subtlety here that this SU2R is actually a filtration and not just like a grading, because like if you take normal ordered products of two objects, the R charge of that object in the VOA can be less than the sum of R charges, that is R1 plus R2. So this NO belongs to this direct sum. So this will be important when we discuss the classification. This is in fact the filtration and not a grading. So this is I'm showing you just a quick dictionary between the SCFT and the VOAs. So in this case, the Schur index of this SCFT is equal to the vacuum character of the VOA. So for example, the Schur index is trace over this quantity, and the Schur index is a trace over this quantity. And using the relation I showed on the last slide, which is this H is E minus R, you can show that it's basically the same thing if you compute it. Similarly, if you have additional grading, if you already know the R filtration of the 4D SCFT, then you can refine your index a little more using a additional T, which we will call by this T. And then you have, this corresponds to what is called the the McDonald index of the SCFT. So this has slightly more information than the Schur index. Now, then there is this conjecture that the Higgs branch is related to the associated variety of the VOA. I will discuss it in the next few slides. And then if you Higgs the superconformal field theory at the level of VOA, this corresponds to what is called the Drinfeld-Sokolov reduction of the VOA. And then the 4D and 2D central charges are related to each other in this simple manner. Okay. So any questions up to this point? It was basically a review.
You said if the R filtration is known in the previous slide, but does it not kind of come from the, like, can you not get it from the theory that you're constructing the VOA out of?
Yes, you're right. If you know what the 4D theory you start with, you know what the R filtration is. But if I hand you the
VOA, so just some VOA and now have a look.
And now it's not obvious. Fine.
Okay, I see. Thank you.
So now in this slide, I'm going to discuss what is the Higgs branch conjecture. So the Higgs branch conjecture associates, like it's a way to extract the Higgs branch as a variety from the VOA data. So in this case, what we do is we define a commutative algebra, which we call RV. This is also called the C2 algebra. And it is defined as taking the operators in the VOA and quotienting it out by any operator that has any derivative or at least one derivative. So this RV will become a space of operators which has no derivatives in it. It has been quotiented out by operators that have at least one derivative. And then one can, and then the thing is this RV in general is not reduced. it means it can contain objects which are like nilpotent. And then if you quotient out the nilpotent operators, what you are left with is the Higgs chiral ring. And the spectrum of the Higgs chiral ring gives you the associated variety, which was defined by Arakawa in around 2010. Okay, so I'll give an example to illustrate how it works. For example, consider this Argyros-Douglas theory, which is A1, A2. It is also called the H0 theory. It is probably one of the first Argyros-Douglas theories found using, I think, SU3 super angles. So the corresponding VOA for this theory is just the the chiral algebra of the 2,5 minimal model, and it has central charge -22/5. And this theory has no Higgs branch. So this procedure that I described here should give you, like, the associated variety should be just a point. So let's see how it works. So if you take the stress tensor, this is the standard OPE of stress tensors, and then there's a null associated in this at this central charge. So as in this procedure, I explained that you have to define RV, you have to quotient it out by the derivatives. So if you quotient out this derivative, what you are left with is a relation that is t square equal to 0. So RV is basically generated by this t quotiented out by this relation t square. So this is there is no derivative in this whole RV. And then the procedure also asks you to quotient out the nilpotence. So since t here is squares to 0, it's a nilpotent, and then you quotient it out, you are left with just C, and the associated, like, the spectrum of this thing is just a point, and which is which is like the same thing as saying there is no Higgs branch in this theory. So yeah, this is the example, like the very basic example that I wanted to share. So as a consequence of this Higgs branch reconstruction conjecture, the vacuum character of this VOA actually solves a modular linear differential equation. So if you don't know what is the MLDE, it's not really important today, but you can think of it as some differential equation formed out of, like, modular forms. And the Schur index actually solves such a differential equation as a consequence of this Higgs branch conjecture. The reason being that Arakawa and Kawasitsu actually established that there exists an MLDE for all the quasi-Lees VOAs, and the quasi-Lees VOAs are basically all the VOAs that come from 4D. We expect them to be quasi-Lees, where quasi-Lees is a condition that there are finitely many symplectic leaves, and of course, if the Higgs branch conjecture is true, the VOAs should be quasi-Lees. And Arakawa Kawasitsu showed that if that is the case, then you are going to get an MLDE that solves. So a possible approach for classification would be to arrange theories using these order of these MLDEs. So take the order of the MLDE, then in increasing order of this MLDE, you try to classify theories. So this was suggested in this paper by Chris and Leonardo, and this was actually done to some extent by Mario, Chris, and Mitch Weaver in 2022. So in this case, like, a systematic scan of all possible solutions of, like, a generic low order MLDEs were made, and by imposing, like, really physical conditions, for example, the solution should have integer coefficients in Q series and things like that, and also some consistency condition on the A and the C anomalies, which comes from conditions on, like, Coulomb branch geometry and things like that. So this was done earlier. In this paper, we propose to organize theories in a more intrinsic quantity that is more intrinsic to the VOA, and which we will call the nilpotency index. Okay, so I'll stop for a second here if there is any question. Maybe it was too fast. If there's no
So far,
question.
so good.
So far, so good. Okay. So let's go on. So let me define the nilpotency index. The nilpotency index is defined as the smallest positive integer n, such that this t to the power of n is actually 0 in RV, which means in the VOA, there is a null state of this form, t to the n plus something, which I call phi, and this phi is in C2V. So a few slides ago, I described what was C2V. C2V is the space of operators which has at least one derivative. So for example, this was basically, for example, this is an example of such a null. So where phi is this del square t. So in favorable cases, the MLD that I described, I just like said a few words in the last slide, arise from the existence of this null. And there is a way to get it from this. You have to do some recursion relations on the vanishing of the torus one-point function. Since this is a null, the torus one-point function should be 0, and then you do a series of steps and you obtain a differential equation because this t will be acting like a derivative on the whole thing. And generically, one would expect from this sort of argument, it is expected that the order of the differential equation is actually greater than the nilpotency index. So there can be, so suppose you start with some null. This null may or may not give you a differential equation. There may be a differential equation at a higher power of t that will correspond to this null. And also there is a possibility that there is a differential equation of order that is lower than n. But so far we don't really observe such a phenomena, but there is no way we can eliminate that possibility. But we expect that this is generally true.
Could it be that the nilpotency index is infinite in some examples?
So if it is infinite, then it would mean that the stress tensor is not nilpotent. Right. And that would basically mean that the Higgs branch conjecture is wrong. So because the stress tensor comes from a multiplet which is not the Higgs multiplet. So everything that should survive should be a Higgs branch operator.
Okay.
So what we did was we computed this nilpotency index in several examples. And in simple examples, we observed that the rank was exactly equal to this nilpotency index -1. So this is like a slightly surprising relation between two quantities which are defined on like two different kind of objects. So the left-hand side is like a Coulomb branch quantity, and the right-hand side is a VOA quantity, which you can also say that, okay, it's like a Higgs branch quantity. So, but as we computed like more complicated examples, we found that this equality is violated, but it's violated only in one direction. So this n-1 is always greater than equal to rank in all the examples that we have observed. So this is something similar, which was not similar, it's a different thing, but Cordova-Shao, like in 2005, had conjectured that the Schur index was equal to the trace of this wall crossing invariant quantity, which counts massive BPS particles on the Coulomb branch. So it's in that spirit, and like a lot of the research in this direction is like motivated by finding such kind of relations in this way between Higgs and Coulomb branch. So to like just recap what I said, so if you have a 4D equal to 2 SCFT, there are two branches, the Coulomb and the Higgs branch. The Coulomb branch is related to the Seiberg-Witten geometry. The Higgs branch is related to the VOA. And it has been shown that, not shown, like it's conjectured that the wall crossing invariant gives you, the trace of the wall crossing invariant gives you the Schur index by Cordova and Shao. And the vacuum character, as I discussed a few slides ago, is the Schur index. So, but there is no like clear direct relation that is known between these two branches. Then we also, as we did these calculations, we also observed that this quantity is somehow RG monotone, which means that whenever you compute it in the IR and the UV nilpotency index is always greater than the IR nilpotency index. So, this kind of conjecture actually implies the conjecture I showed a few slides ago, that rank is less than n-1. This can be shown very simply by noting that for any theory, you can move on a very generic point on the Coulomb branch, where you have just free vector multiplets. And it can be shown, although I have not shown it, it's very easy to show that the nilpotency index for the free vector multiplets, rank free vector multiplets, is just rank plus 1. So if you put it in this inequality, you will get back this inequality, that n-1 is greater than or equal to that. Also, this conjecture can be made a little more sharper for mathematicians by saying that there's a procedure called TS reductions for VOA, which correspond to Higgsings. And then if any VOA that comes from a 4D unequal to SCFT, in that case, after a DS reduction, the nilpotency index should be lower or equal to the starting nilpotency index. So we believe that this is actually not a conjecture, but can be proven based on facts in mathematical literature, although we don't have a very sharp statement, but it can be shown, I think, using the fact that the associated scheme after the DS reduction is actually an intersection with the Slodoi slice. So the scheme actually becomes smaller after a DS reduction, and we expect that you can use that to show that indeed this is actually true more generally in all the DS reduction cases. So to get a feel, let's do the most simplest example, that is K-free hypermultiplets. So the VOA for K-free hypermultiplets is just K copies of beta gamma systems, where each of them has weight half, and their OPE is the standard beta gamma OPE with this delta function, such that it's one only when they are the same hyper. So the stress tensor in this VOA is actually not an independent generator, but it's actually like a composite made out of these beta and gammas. And using what I said earlier, you have to quotient out the derivatives. So after modding out these derivatives, you're left with t equal to 0. So in RV, t is 0, and the nilpotency index is 1, therefore. And the order of the differential equation for this theory is also 1. So it satisfies the inequalities I showed earlier. So now I'll do an example which is slightly more involved and also show this UV-IR thing. So let's consider this conformal SU2 super QCD. The associated VOA is just a fine Kac-Moody algebra of SO8 at level -2. So this has generators in the 28 of SO8 and with the usual AKM OPs. And the nilpotency null in this case is of this form, where this part you already saw in the A1, A2 Argyros-Douglas theory. Now we have also contributions from the J's of this VOA. And again, if you quotient out these derivatives, you have t square equal to 0 in this RV, and the nilpotency index is just 2. So this satisfies this rank conjecture. In fact, in this case, it's an inequality because rank of this theory is 1, and 2 minus 1 is 1. Then you can also try to do the following. You can Higgs the theory. So if you Higgs the theory, you are left with just free hypermultiplets. And in the infrared, this is 1, as I showed in the last slide. So again, this also is consistent with this inequality of UV and IR. So just to recap, so these are the main conjectures of this paper, where the nilpotency. Yeah. Yes. Please go ahead.
Just to be clear about what you mean by NIR, it's N if you go out Higgs to the Higgs branch, or if you go down to the Coulomb branch. I mean,
oh, this Higgsing is moving on the Higgs branch.
The Higgs branch, but in general, you'll just say no matter how you Higgs, whether it's a Higgs mixed Coulomb branch, NIR is less than or equal to NUV.
Yes, the general statement is that this is true for any RG flow, not just Higgsing, like moving on the Higgs branch. Even if you move on the Coulomb branch, this should be the case. In fact, that's why I said that if you move on a generic point on the Coulomb branch, the first conjecture is actually a special case of the second conjecture, because then the IR n is actually rank plus 1. So rank plus 1 is greater than or equal to the UV n, which is basically the same inequality.
Thanks.
Thank you for the question. Okay, so I think I said this right now, what I wanted to say on the slide. There are these two conjectures, and in like rest of the talk, I will just give you examples, and finally I will show classification of theories using this n. So let me just discuss briefly what the methods were used to compute this. So first method is a very direct method. In this method, we would start from the presentation of the VOA in terms of its generators and its OPEs. And then we do a systematic search of the nulls. Like you write all the possible operators, and then you try to find norms, and then you see, okay, this one is 0, so it's a null. So that's a systematic search you can do, but the issue is that as the n becomes larger, it becomes really, really harder to compute these norms, because you need really more computational power to find the null. Then second way of finding this thing is to use the free field realization. So these free field realizations are basically expressing generators of your VOA in terms of composites of free fields. So a very simple example would be if you take the beta gamma free field system and you consider the composite beta gamma normal ordered. This object, if you compute its OPEs, it behaves like a U1 current. So in this case, the U1 current is like has been given a free field realization in terms of beta and gamma. Other free field realizations are more involved. And the advantage of these free field realizations is that whenever you have a null, the null is exactly equal to 0 once you insert the expression in terms of free fields. So if this gives some advantage to some extent, and then you don't really need to compute norms, you just need to express each object as a free field, and then you see, okay, is it 0 or not? If it is 0, then it's a null. And the third one is slightly indirect. In this case, we look at the superconformal index. So as I discussed earlier, the McDonald index is equal to this graded character of the VOA. So what we will do is we'll take this index and take a platheistic logarithm of it. I think in this audience, everybody knows what a platheistic log is. But very roughly, it gives you an expression in terms of generators minus relations. So it will give you all the generators of the VOA and minus the nulls. But there's some subtlety there, so I'll do an example to explain. So let's consider again the simplest example I discussed. So the stress tensor OPs are given here for A1, A2 theory, and the nilpotency index is 2. And also this is a rank 1 theory. So yes, so it's rank plus 1 is equal to 2 in this case. Okay, so so I'm not going to discuss the free fields because it's really involved and it's a different direction, but I will quickly tell you how to do it from the superconformal index point of view. So if you take the platheistic log of this McDonald index, you get an expression like this. Over here, I've taken out this 1 minus q because this 1 minus q has the interpretation of adding derivatives to your VOA operators. So I've removed all the derivatives by dividing it by 1 minus q. So what is left over should be roughly generators minus relations. So the first term, as you can see, is q squared t. This is our stress tensor. So it has weight h. The weight power of q is 2, and this power of t is 1, which means that the r charge is equal to 1. This is correct. So this is the stress tensor. Now, if there is a null that is t squared, it should contribute as like minus of q to the 2k times tk, depending on what power of k is there. In this case, the k should be 1. So you should find null at q4 t squared, which is precisely this red colored object that is the null.
Could you remind me what t it means in the index? Sorry.
So in the index, this t was actually counting r charges, and this u1r also. So the stress tensor has a u1r equal to 0. So if you have a null of this sort, it should contribute in this form.
Okay, thanks.
And then there is this usual subtlety of the platheistic log, where there are additional terms which sort of take into account relations among relations and things like that. So this analysis can get really complicated if the index is not flavored. It means like if you don't refine it with, let's say, the flavor symmetries of the theory, and so it can get complicated, and also it gets polluted by these extra terms, which I think these algebraic geometry people call CCGs and stuff like that. So yeah, let's do a slightly more involved example. Again, we'll take this simple SU2 super QCD, which is conformal, and the VOA in this case is SO8 at level -2, which has this standard OP. And in this case, the null vector is of this form. I think I already showed this. So let's see if we can identify it in the platheistic log. So the first 28 times QT, these are the J's. So the J has weight h, so q to the 1, and it has an r charge 1. So it's 28 QT. So this is good. And then we want to find the null of the form which I showed here, which is like 2k t to the k. And you can see it's here. No other term looks like that. And indeed, it is t squared term. So this way you can like try to identify or make like at least an educated guess as to what the null is. Also, if you have like a completely refined index, then this is like very easy. It's not very easy. It's more easy to identify this null because then this is a singlet under those symmetries. Okay. So very good. So these are the results that we had. It's a long table. In most examples that we have checked, you can see that it's actually equal. Like in this rank is actually just equal to n plus 1. So it kind of saturates inequality in all these simple examples. And similarly, the order of the differential equation is also satisfies the inequality I showed. It's greater than the nilpotency index. So there are a few colors here. Don't get distracted by these colors. It's just that this yellow one are the results which we have given based on the analysis of McDonald index. Here we have not found an explicit null. As I said, McDonald index thing is not like 100% clear that there is a null there, but this gives an indication. So that's why these are all in yellow. And these orange ones are theories where these come in series. So for example, this A1 D2n plus 1 with different n belonging to positive integers, there's a theory corresponding to that. Now, In this case, we could not, of course, compute or show very generally what these values are, but we have computed it in a bunch of examples, and based on those examples, we conjecture what the general form of this for this whole series will be. And rest of the white ones are the quantities that we have computed. We found a null, and those results are written here. And one place where you can see the inequality being violated are these genuinely unequal to 3 theories. Rank 1 unequal to 3 theories with these moduli spaces. These are the Higgs branch. And in this case, you can see that the nilpotency index is 3, and the rank is actually just 1, 3, and 4. Okay. So then we also tried to do this analysis for rank 1 theories, but it was not. It becomes very hard as soon as the UA becomes more involved. So as I said in the beginning, these were like classified by Philip, Mario, Lotito, Lou in 1516, and Chris, Mario, Carlo, Leonardo, and me worked out the corresponding VOAs for all these theories very recently. So these VOAs are quite complicated, and it's hard to really compute what the index is, but based on some classification and some checks, we have been able to at least rule out the fact that the nilpotency index for some of them is not at least 2, for example. So if it's not 2, it's greater than 2 definitely, and so on. So let me say a few things about this table. So this table contains like all the rank 1 theories, and they are divided into a few blocks, and theories within each block are related to each other. For example, this theory, an RG flow, there's an RG flow connecting C5 to C3A1 and so on. So you can go down the RG flow in each block. And so the first one is the Deligne rank 1 theories. These are uniform series of theories which are labeled by the Lie algebras, which are called Deligne rank 1 series. So these contain H0, H1, H2 theory, if you know them, and also the E6, E7, E8 Minhan-Machinsky theory, and it also has the SU2 super QCD. All these theories have the nilpotency index equal to 2. Now, the theories in blue are n equal to 4 is the n equal to 4 superangles. This also has n equal to 2. And the ones in green are generally n equal to 3 theories, for which we computed, at least for these two cases, that n is 3 and 4. And the way we eliminated the other cases, I will explain when I discuss the classification. So the conjecture seems to be, all the conjectures that we say seem to be at least correct so far, and no violations have been found. Okay.
I ask, for instance, in the 2-star A2 guy, your conjecture would be then that n must be greater than or equal to 4 to
yes, that would be the conjecture, but we could not go that high. We could just eliminate the fact it's not 2.
Sure.
Okay, so now let me discuss, give you basically a few examples of RG flows. It's mostly a conjecture. So again, the UV n should be greater than or equal to the IR. There are two classes of RG flows that we discuss. The first one is like you do a relevant deformation and then you also tune your Coulomb branch parameter so that you land on the correct SCFT in the infrared. And the second kind of RG flow that I'm going to give examples for are Higgsing. Higgsing means giving a web, moving on the Higgs branch, basically giving web to Higgs branch operators. In this case, there are sometimes usually you find interacting theory and a bunch of free theories along with the interacting theory. So I'll give examples that will make this clear. So for example, in the case of flows in which you do a relevant deformation and also tune the Coulomb branch parameter, The simplest one is this Deligne rank 1 theories, which I said were labeled by these Lie algebras in this series, and all of them are literally like have n equal to 2, so there is no violation here for the for that conjecture. Then you can also consider these Argyros-Douglas theories, which are labeled by two integers k and n, and there is an RG flow where this n actually decreases by 2. So this is one example. A1, A2n goes to the lower one. So the nilpotency index goes from n plus 1 to n, and so on. So this is like a bunch of examples just to show that this works in quite a number of examples, but not a lot, but significant number of examples. Then this is a set of examples for the Higgs-in case. So you move on the Higgs branch. So for example, if you take Deligne rank 1 theories, you just find free hypers in the infrared. And for Deligne rank 1, the UV was 2, nilpotency index was 2, and the infrared nilpotency index was just 1. For n equal to 3 rank theories, you find a bunch of free hypers and free vectors. So if you have a bunch of free hypers and a single free hyper and a single free vector, the nilpotency index is 2. So in all these examples, there are these decoupled free sectors. And so in this special case of Deligne rank 2, D4, in the infrared, you have 2 copies of Deligne rank 1 and a free hyper. So now you need to just be a little careful and find the right nilpotency index. So if you have a bunch of decoupled theories, you can define the stress tensor by the diagonal sum. And then you can, there's a very simple argument that will show that for the tensor of theories, this is the correct formula for finding the nilpotency index, where if you have k such theories, you just take the sum and subtract k minus 1. So in this case also, all of them you can see the UV is greater than IR. And in this Deligne rank 2 D4 case, it's if you don't use this thing correctly, you will not get the right answer. So in this case, it's actually 3 goes to 3. So over here also, this UV IR works. Very good. Okay, so I still have like 15 minutes, so I think I can actually go over the classification. If there is any question, I can take those. Okay. So if there are no questions, let me carry on. So if the conjecture 1 was correct, the nilpotency index is supposed to provide a measure of complexity of these 4D n equal to 2 SCFTs, which presumably is more refined than the rank because of the inequality that I showed. So for a given rank, you can have a lot of nilpotency indices. So this suggests a natural program to classify these theories from the point of view of this nilpotency index. So what we'll do in the remaining talk is to classify theories with n equal to 1 and n equal to 2. And we'll use a mild assumption for the R filtration of the corresponding VOAs, which I'll state in a few slides, in the next few slides. And under this assumption, the n equal to 1 theory, the only theory is the free hypers. And for n equal to 2, the only theories are these Deligne rank 1 theories and the SU2 n equal to 4 superangles. So the strategy is to first list all the operators that can show up in this null. So you have t to the n, and then you have to write down all the possible operators that have at least one derivative and have the same conformal weight and are uncharged under any flavor symmetry, such that this object is a null. So imposing the fact that this is a null and also using 4D unitarity, we can really restrict all the possible theories for this n equal to 1 and n equal to 2. So first of all, let's start with writing down all the objects that can show up in this null. For example, at weight half, so over here I'm using the multiplets, labeling the multiplets by notation used in Dolan and Osborne. So all the B hat multiplets are Higgs branch multiplets. So let me just quickly go over them. So for example, at weight half, it's just free hypers. At weight 1, you can have flavor currents and you can have free vector multiplets. At weight 3 halves, you have this weight 3 half Higgs branch generator, and then you also have additional supercurrents. That's why they are labeled in green. And if you have any such operator in your theory, you are bound to have enhanced supersymmetry. So you will go from n equal to 2 to n equal to 3 or 4 if you have this multiplet in your theory. And for weight h equal to 2, there is a weight 2 Higgs branch operator. And of course, the stress tensor, which I discussed at weight 2, is also here. So these are all the possible operators that you can have if you want the nilpotency index to be 1 or 2.
Do you easily see whether it's n equals 3 or n equals 4 enhancement when you have these green guys?
Do you easily see? So these will be like the way the multiplet structure is organized. For n equal to 3 theories, if you write it as n equal to 2 theory, you will always find these extra current generators. So it's a representation theory logic. That's what I can tell you.
Okay.
Okay, so let's do the simplest example, n equal to 1. What can you write? So from this list of operators that I wrote, you have to write objects which have weight equal to 2. So this is the only thing that is possible that you can write in a way that this object is a primary, because nulls are supposed to be primaries. And that's it. There's no other option. So the only theory with n equal to 1 is the free hyper. And let's now, n equal to 2, it becomes significantly more complicated to do it. So for the most schematic, the schematic form for the most general null is of this form, where let me just remind you, this is of course the stress tensor. These J's are the AKM currents. These G's are the supercurrents, and these W's are weight 3 half Higgs branch operators. And this O is a weight 2 Higgs branch operator. So the starting point of the analysis is to, okay, let's impose the condition that it's a Virasoro primary, because it's a null. So if we impose this condition, the first 2 terms are the standard conditions for the Virasoro primary, but then this order 4 pole should actually vanish. The vanishing of this order 4 pole will impose the following. So this is O. Let's assume if this whole thing is a null. If this is a null, it basically means this O is actually not an independent generator, but is equal to this T plus J square, which is by assumption not the case. We are assuming O is an independent generator. Therefore, the O cannot appear in this expression. So this term is gone. Then what we are left with is T is proportional to J square. And this is like a very standard condition for what is also known as the Sugawara condition. In this case, the stress tensor is a composite of the AKM currents. And this basically imposes constraints on what the central charge K and C are for the theory if the stress tensor is a Sugawara. So in conclusion, the first condition is that if n is 2, the theory should have a Sugawara stress tensor. And if the central charge is not 22, minus 22 over 5, in which case we have already discussed it's the H0 theory, which has no flavor symmetry. Okay, so let's first do the case of n equal to 3 and n equal to 4 theory. These are much simpler to handle. So if you have an n equal to 3 or n equal to 4 theory, the corresponding VOA has a sub VOA, which is the n equal to 2 superconformal algebra. And if it's n equal to 4 SCFT, it's called the small n equal to 4 superconformal algebra. In both cases, these algebras are generated by the stress tensor, the affine Kashmuri currents. the supercurrents, and then you can also imagine you can have like a W generator if you want to write a null of this sort. So here the T is the stress tensor, and this J is U1 or SU2 depending on whether you have n equal to 3 or n equal to 4 supersymmetry. So if you have n equal to 3 supersymmetry, this J can only be U1, and if you have n equal to 4 supersymmetry, this J can only be SU2. And then there are these supercurrents, and the central charge for these theories have to satisfy this relation, that is C is equal to 6K, where C is the central charge associated to the Virasoro algebra, and K is the central charge associated to the affine Kashmiri algebra. So imposing, first of all, in n equal to 3, the Sugawara condition, you will get T is J square. And in that case, the central charge has to be 1 if you use the OPs of this J square. And this is not possible because in the correspondence basically implies that whenever you have a unitary 4D SCFT, this 2D central charge has to be less than 0. So the C equal to 1 case is eliminated. So there is no n equal to 3 theory which has n equal to the nilpotency index equal to 2. And also I gave a few examples for the rank 1 n equal to 3 theories where it was computed to be like 3, 4, and so on. It was not 2 for any of those. Then we come to n equal to 4. In n equal to 4, the Sugawara condition will actually give the following constraint on the central charges. You can combine this constraint with the fact that the n equal to 2 and n equal to 4 superconformal algebras have this C equal to 6K. Solving for this gives the only answer is C equal to -9. And this this central charge and BOA corresponds to the n equal to 4 superangles with gauge group SU2. Now, it is shown that this you cannot extend this more, by which I mean that you cannot have like these additional W kind of objects in it. So if this cannot be extended more, this is the only theory that you can have with this nilpotency index 2 is the n equal to 4 superangles. So this Sugawara condition is actually quite constraining in this case. Now, next we'll make a minor assumption regarding this. So there was this very general form of n equal to 2 null that I wrote. In this case, we had eliminated the del square O, and this del G is also eliminated because these were the cases when you had enhanced supersymmetry. So now we are only left with this term, and this del W term. So we'll assume the following about this del W term, that this term will have R charge equal to 3. So this W generator in itself, we know where it comes from 4D. It has R charge 3/2. And since it was a filtration, the composite can have R charge less than or equal to 3/2 plus 3/2, which is 3. But we'll make a slight assumption that this cannot happen. And indeed, we have checked this assumption for all rank 1 theories. This does not actually happen. So assuming there is no drop in the R filtration, the only possible null that you can write is this. The reason being, if this has R charge 3, the stress tensor has R charge 2. So R charge 1, sorry. And the square of the stress tensor is R charge 2. So you cannot cancel a term with R charge 2 with a term that has R charge 3. So with this assumption, this is the most general form of the null that one can write. Okay, so there is a very small aside that is important, that so now you can obviously see that there are just two generators, the stress tensor and the affine Kashmiri currents, and the stress tensor is a Sugawara stress tensor. So now the question comes up: what are the possible AKMs that can land in this case? So the first thing which we'll show is that the only AKMs that can land in this case have to be simple Lie algebras. If the Lie algebra is a direct sum like this, it is not possible. This will follow from the Sugawara condition. So if you have a direct sum of two simple Lie algebras, the stress tensor is basically the sum of individual Sugawaras, T1 plus T2, where each Ti is proportional to J square. Now, if you take a T square, this is the expression you get. In this case, as you can see, this T1 times T2 can never belong to an object that has derivatives in it, because these two never talk to each other, and so you cannot actually find a way to make it belong to the space of operators which has at least one derivative. So therefore, anytime you have a direct sum, the algebra is simply it's not possible. You have to have a simple Lie algebra. So if you have a simple Lie algebra, that's it. You start with writing this most general null, and imposing that it has zero norm because it's a null. You will find these are the following coefficients you can have, where HV, Hcheck is the dual Coxeter number, and this case is the affine Kashmiri central charge. Now imposing this fact that this was a null, and also the fact that there's a Sugawara stress tensor, you can solve these conditions, and you get this simple equation which defines the central charges in terms of Lie algebra data. So next step is to simply go over the list of all possible simple Lie algebras and impose that the central charges are rational. This is a fact that has been shown recently by Leonardo and Brandon Ray Horn, that the 4D n equal to 2 central charges are rational. So you go over the list of all simple Lie algebras and impose that things are rational, and also impose 4D unitarity bounds. This will restrict you to simply Deligne rank 1 SCFTs, and no other solution is possible. Therefore, under this assumption of this R filtration, we have shown that the only theories are Deligne series theories and SU2 n equal to 4 superangles. So that is it. I'll just conclude with a few summary points. So we have two main conjectures. First is this rank is less than or equal to n minus 1. This hints something like a VOA and Coulomb branch structure correspondence, but what is deeply inside is not clear. And then we also found that this was like the RG monotone. It decreased under RG flows, and under this R filtration hypothesis, we classified these theories. It would be interesting to do it for n equal to 3, and so on. So that's like a future direction that one can try. So that's it, and thank you.
All right, let's thank Anirudh.
Thanks.
Questions?
No questions.
It was all very clear.
I have a kind of a vague question, which is, do you think that this can sort of shed light on the question of whether there could exist an interacting rank 0 theory, n equals 2 theory?
Oh.
Interacting rank 0 theory. Yeah, this thing. So if you have a rank 0 thing, then what is the thing? So if your rank 0, n has to be greater than or equal to 1. So at least if it is a rank 0 theory that is interacting, it has to have nilpotency index greater than 2, because we have already kind of classified it for n equal to 1 and 2. So if it is there, we have to show at least it has to have nilpotency index higher.
Right. So maybe I could ask it a different way. Let's say you're trying to do a classification at, say, at n equals 3. How much does the complexity kind of explode as you just go up in n?
It will increase very, very rapidly, because as you can already see in n equal to 2, we had the most general form was like this. In
Right.
more, if you go to n equal to 3, you are actually working with dimension 6 operators. So as you go in n, the dimension of the operators is like 2n.
Right.
And now you will also have operators in some representation of this j, which will make it like even more complicated, so on. So you will, it really becomes very complicated. But I mean, it's not impossible, but it would involve a lot of hard work.
I'm just wondering if there's some way of seeing that at some n, there's kind of room opens up for the existent. Anyway, I don't know.
Yeah, we thought about it, but yeah, we really don't know what's the best way to do it.
Okay, thanks.
Thank you.
More questions?
I guess a related question. So you argue that there is a minimum value for the nilpotency index given a rank. Do you also expect that there is some maximum value? Say you want to study theories of fixed rank, you expect that n is also bounded from above? Like,
oh, okay. I really don't know. I don't know. Maybe it's possible, but I have no idea about this thing.
I see.
One thing which you can do, of course, the way to bound it would be the following. So if you start with a theory, look at all the theories that are above in the flow. For example, so let's take this example. So if you know what possible UV theories it can come from, so let's say you start from the IR, sorry, this flow, for example. So let's say you are here somewhere and you know that all the theories above have some nilpotency index. These nilpotency index you can probably use to bound the theories index in the IR. So if you already know where the flow starts from.
I see, thanks.
Okay.
Any more questions? Okay, I would say then let us thank Anirudh again.
Thank you.
And we can go off the record.
Yeah.